In the last lecture, we discussed the basic philosophy of frequency sampling and we distinguished between odd length and even length. The samples are different, and we gave a general expression for the system function. That is, we said that you do not have to compute h of n from h of k, you do not have to compute. Once you sample capital H capital H d of e to the j omega at capital N number of points, that is h k equal to h d e to the j 2 pi k divided by n, then conceptually you come back to h of n from h of k, then you compute the system function and so on. But you can do this without computing h of n, and we showed that the system function h1 of z can be written in the form 1 minus z to the minus n divided by capital N summation k equal to 0 to n minus 1 hk directly from hk from the samples, 1 minus e to the j 2 pi k divided by n, then z inverse. And we are also tempted to interpret this as a parallel connection of first order blocks with, of course, complex coefficients, but then we desisted from that because poles are on the unit circle. Therefore, this expression, the utility of this expression is not in realization, but in finding the frequency response, that is h1 of e to the j omega. And we can simplify this further by writing h1 of e to the j omega as equal to 1 minus e to the minus j omega n divided by capital N k equal to 0 to n minus 1 h k divided by 1 minus e to the j 2 pi k by n e to the minus j omega, which I can write as e to the minus j omega n by 2, the usual trick. I take this out divided by n, and then in order to bring some symmetry in the numerator and denominator, I take this inside the bracket once more, hk, I get e to the j omega n by 2 minus e to the minus j omega n by 2 divided by, from this I take e to the minus j omega by 2 minus pi k by n, so that I can bring a sine term and you see this will be twice j sine of, yes, omega by 2 minus pi k by n. Is it clear? And I cannot take this out because it depends on the summation variable n minus 1. I cannot take, let us change the color, I cannot take this term out, but I can definitely take this out. And then what do I get? I get the familiar expression e to the minus j omega capital N minus 1 by 2. I asked for a linear phase, therefore the phase term must come out. The rest of it must be real. Okay? So, this becomes summation n minus 1 k equal to 0, then in the numerator I shall have h k, yes, but you have to bring this out also, e to the minus pi k by n. So, it is e to the j pi k by n, then sine of omega n by 2 divided by sine of this 2j and 2j will cancel from the numerator and denominator. Okay. It is a minus j pi k by n. Yes, correct. Divided by sine of omega by 2 minus pi k by n. Now, this expression can be put in a more elegant form by noticing that if you write sine of omega n by 2 minus k pi, okay, when k is 0, this is equal to sine of omega n by 2. When k is 1, it is equal to minus of this. When k is 2, it is again plus, and therefore this is equal to minus 1 to the power k sine omega n by 2. Is that okay? Is that okay? Therefore, I can write my transfer function, the frequency response function, in this elegant form, e to the minus j omega n minus 1 by 2, this is expected divided by n. In the summation then, k equal to 0 to capital N minus 1, excuse me, the numerator I can write as minus 1 to the power k h k e to the minus j pi k divided by n multiplied by sine of, in the denominator, omega by 2 multiplied by sine of omega by 2 minus pi k by n, and in the numerator I get the same argument with a multiplication by capital N. Isn't that right? I should have sine omega n by 2, but I have shown that sine omega n by 2 is minus 1 to the k multiplied by this. So, sine of omega n by 2 minus k pi. Agreed? So, it is of the form sine of capital N theta divided by sine of theta. That is the elegant form, and this is the form that should be utilized for computation of the frequency response function, unless capital N is very small, maybe it consists of 1, 2 or 3 terms, then you do not bother. Okay? When will it consist of 3 terms only? When will it consist of 3 terms only? What should be the length? 6? No? All right, think about this question. If capital N is small, then you may not have to use this expression. You can use directly h of n and then the frequency response function. Okay? This is to be used when capital N is large, and obviously you shall have to write a program. You shall have to compute this by a software routine, and except for this term, the rest of the term is assured to be real, because it is the pseudo magnitude. Why? Because by assumption we designed a linear phase filter. Okay? Our starting point was that the filter is linear phase. That is why we had H, capital H of k equal to capital H star of n minus k, complex conjugates, and so on. Now, there are some situations in which this sampling procedure cannot be used. K equal to 0 to n minus 1, it cannot be used. Why? Because at k equal to 0, k equal to 0 is a problem. For example, if our is to realize an approximation to 1 by j omega. What is 1 by j omega? It's an integrator, isn't that right? An integrator has the transfer function 1 by s. Suppose we have to design a digital integrator, an approximation to a digital integrator, then obviously we cannot use omega equal to 0 as one of the sampling points, because at that point the magnitude goes to infinity. Agreed? There are other situations when this is true, and therefore we cannot take this sample at omega equal to 0. In other words, we have to take a sample slightly shifted close to 0 but not at 0. The scheme that we can use is 2 pi k plus half divided by n, where k goes from 0 to n minus 1. Okay? This sampling scheme is called type 2 design, type 2 frequency sampling design, FSD, and this scheme is called type 1 frequency sampling design. Okay? If you use this design, obviously the first sample would be at omega equal to pi by n, isn't that right? Okay, instead of 0 it would be at pi by n. In other words, the sampling domain would be not here, but the first sample would be here, where this angle is pi by n. Then the next one would be here, where this angle is 2 pi by n. Agreed? And so on. You go like this. The last sample would be here. Once again, this angle is also pi by n. This is the last sample, and this would be 2 pi, yes, 2 pi minus pi by n. Agreed? 2 pi minus pi by n. This will be last sample. Now, because of this sampling scheme, there is no capital H of 0. So, we do not have to have a real term. Agreed? In the previous scheme, capital H of 0, because k equal to 0, e to the power j 0 is 1, therefore capital H of 0 was required to be real. It had no matching term. But here we can match every term except when capital N is odd. Then we shall be left with one odd term, which for reason of linear phase constraint must now be 0. In the previous case, when capital N was even, the middle sample capital H of n by 2 was required to be 0. Here, when it is odd, it is required to be 0. That is, for H of n to be real in type 2 design, we shall have for n odd, the conditions are capital H of n minus k minus 1 should be equal to capital H star of k. Do you see the difference? In the previous case, capital H of n minus k was required to be H star of k. Okay, here it is n minus 1 minus k, and in addition the middle term n minus 1 by 2 should be equal to 0. Whereas for capital N even for type 2, the condition simply is complex conjugation, nothing else. There is no middle term, H star of k. Capital N even, you have even number of matches. Every term has a match. Okay? So there is no middle sample, there is nothing to be required to be 0. And when these conditions are satisfied, you can write H of n, the impulse response, as equal to, obviously it shall be different for capital N even and capital N odd. Now in this case k goes from 0 to n minus 1 by 2, then minus 1, because n minus 1 by 2 is 0, right, this condition. What is this equal to? N minus 3 by 2, right. And here it goes from 0 to n by 2 minus 1, n is even. That is equal to n minus 2 by 2. You understand the difference? We require these upper limits in this summation. So when this is satisfied, n times h of n, I bring 1 by n to the left hand side so that I don't have to write this again and again. N times h of n would be twice. Now I don't have a loaner, I don't have a loan term. So twice summation. If I had a loan term, then the loan term has to be written first, but I don't have it here. So n minus 3 by 2, k equal to 0, real part of hk e to the power j pi 2k plus 1 n divided by capital N. Actually it is twice pi by 2n, 2 I have cancelled. This is for n odd, and it is twice summation, all that changes is the summation limit, n minus 2 by 2 as I have shown earlier, multiplied by the same quantity, summation same quantity for n even. If you want to calculate if you want to calculate h of n, you may not be required to, but if you have to calculate, then is it convenient to leave the real parts in the inside the summation, or is it convenient to take the real part outside the summation? Real of a plus b is the same as real of a plus real of b. Okay, so it is purely a matter of computational convenience. Where would you like the real part to be? Outside the summation or in? Why? Because it is easier to sum up exponentials rather than trigonometric functions, cosine and okay. So real part and summation can be interchanged according to convenience. In this case, the transfer function, that is h1 of z, can be, again it can be obtained directly from capital H of k. You do not have to go via h of n, and in this case instead of 1 minus z to the minus n, you get 1 plus z to the minus n. Okay, you get 1 plus z to the minus n divided by n. It can be shown in a very similar manner. K equal to 0 to n minus 1 is the number of samples, hk divided by 1 minus e to the j 2k plus 1 pi by n. Instead of k pi by n, it is 2k plus 1. Instead of 2k pi divided by n, it is 2k plus 1 pi by n, z inverse. And if you put z equal to e to the j omega, then you shall not get sine term, you will get a cosine, and it will be the same form h1 of e to the j omega, that is the the phase term is a linear phase, e to the minus j omega n minus 1 by 2 divided by capital N. Then inside this summation, k equal to 0 to capital N minus 1, hk e to the power minus j pi, what shall you have, k plus half divided by n. In the previous case it was e to the minus j pi k by n, k is now incremented by half, multiplied by, instead of sine you shall have cosine. And then in the denominator you shall have j comes from the sine term, because it is 1 minus this. So, j sine of omega by 2 minus pi by n k plus half. Okay. Keep this in a prominent place. Either this expression or the previous expression may have to be programmed for calculation. Now, let us look at an example. Type 1 and type 2 designs of frequency sampling guarantees linear phase to start with. If you do not want linear phase, then you do not have to bother about while things become simpler as well as tougher. In linear phase you have to compute half the number of terms. If it is non-linear phase, then you have to compute all the terms, but you may be able to do it less number of terms. Do you understand this? If there is no linear phase constraint, then the number of delays to be used may be less. Okay? So, it is an advantage as well as a disadvantage, but one hardly uses FIR if linear phase is not a constraint, hardly ever uses. Okay? Now, an example. Suppose we have to design a low pass filter with this characteristic. End of the base band is 9 kilohertz and this is 1 and this is 5 kilohertz. Okay? 0. This is what we have to design, and it is stipulated that you can use only a length of capital 9. It is stipulated that way. Then in terms of omega, this corresponds to pi and this corresponds to 5 pi by 9. You shall have to have, well, you have to construct the diagram from omega equal to 0 to twice pi and k equal to 1, k equal to 0 to 8, and this diagram, I think I have it here, yes. Can you see this diagram? Okay. So, I have constructed up to, I have continued this here, all right, and this is 9th, this is 2 pi, actually it should have been continued. But anyway, I do not require this sample, I have to go 0, 1, 2, 3, 4, 5, 6, 7, 8 samples, of which I require only up to this. In the summation, you know, half of, not only that, because these samples are 0, I require summation only from k equal to 0 to 2, and k equal to 0 has to be real and therefore only 2 terms. You see the simplicity? Okay. Now, pi is somewhere here. This is 5 pi by 9 cutoff frequency, this is 4 pi by 9, 5 pi by 9, this is 6, 8, in between must be 9 pi by 9, which is pi. You must be careful about this. Okay? You have to construct the corresponding phase, right? What will be the relationship? E to the minus j omega times n minus 1 by 2. So, 4 e to the minus j 4 omega up to pi, and then beyond pi it has to be the other way around. But you do not require that. It was only done for your understanding's sake. for giving you the complete picture. You don't require, you require only these samples. So find out the corresponding phases and that's it. Is the point clear? You do not have to draw the complete diagram because ultimately it's only these 3 samples which are required. Okay, I shall come back to this diagram a little later, so I'll keep it separately. Now, if you do this, then the corresponding HS, all you have to calculate is half of the number, and these will be based on one real sample, that is 1, and 2 complex conjugate samples which will give rise to a cosine. So it's a very simple calculation. Have you followed this? The formula for H of n. Capital N is odd. It will contain only 2 terms in the summation, and it's very easy to calculate this. These are the impulse response samples. I have given a copy, and you have to calculate only half of them because H0 is H8, H1 is H7, and so on and so forth. And if you do that, then the frequency response that you get, frequency response is now very simple. There are only 4 terms and they are complex conjugates of each other, and therefore you can calculate this. You notice that the frequency response, where did we want? Oh, the sampling frequency is 18 kilohertz. So this is 9 kilohertz. 9 kilohertz was the end of the baseband, therefore 18 kilohertz is sampling. 0.5 normalized frequency is shown here. Where should this be? 0.5 corresponds to pi, so 5 kilohertz will correspond to 0.5 multiplied by 5 divided by 9, that is 2.5 by 9, so 0.25 something. Somewhere here is the cutoff frequency, but you see what, pardon me, 0.28, so it's somewhere here, and you see the wide divergence, wide tolerance that you get, okay, and there is a tolerance, this is also pretty wide, 0.2 in the stop band. It's a very bad design, okay. Now exactly as in windowing technique, where we wanted to avoid abrupt transition, we can do that here also. And what we can do is the following. Suppose your low pass filter is required to be ideal from 0 to 4 samples. Suppose this is the required design, then we can intentionally taper it. That is, between the pass band and the stop band, you can allow a transition band which for simplicity has been taken to be linear, okay, and you can include as many samples as you like. This tapering can be from like this, all like this, okay. You can include 1 sample, 2 samples or 3 samples or whatever number you want. Let us see what the effect is. This has also been tried. The effect is we have taken HK as equal to capital N, we take as 15. Not quite. You know, what we require is, if we take capital N as odd, what we require is only these samples, right? We don't require anything beyond this. Now, if this is the pass band and this is half of the, this corresponds to pi, therefore the number of samples would be 29, agreed? 15 times 2, 30 minus 1, 29. So, capital N is 29, but you require only the first 4 if you do not allow any transition, or 5 if you allow one sample in the transition, or 6 or 7 depending on what you want. Is the point clear? So, you do not have to bother about the length is 29. If you do not allow a transition, then it is 1 from k equal to 0 to 3, right. There are 4 samples. If you do not allow a transition, 0, k equal to 4 to k equal to 0 to 4, agreed. So, it will be 5 to whatever you want, okay, not 7, let us say 8, 5 to 8, okay, because we will introduce samples here. Then if you use once no transition band, no sample in transition band, if you use one sample in transition band, you have to do this carefully. And if you allow a linear transition band, then obviously the value would be k1 from k equal to 0 to 3, right, not 4 now, because you are allowing 1 in the transition band. I can do it both ways. I can take the 5th one in the transition band, or I can reduce the pass band allowing a transition band inside. Everything is uncertain, you can try both, whichever works, okay. Suppose we do this, k equal to 0 to 3, then the intermediate sample would be 0.40406, k equal to 4, one sample in transition band, and 0, k equal to 5 to whatever the number is. Or I can do this 0 to 4, I can keep 1, then the 5th one I can allow the value to be this. Who determines the value? The linear fall. So, if you use 2 samples, then in the linear fall the first sample in the transition band would be higher, the next one would be lower, okay. So, you can do this in a very simple manner, and I will only give you the final result. This has been calculated, and the impulse response samples, only half of the number have to be calculated, half of the number. In terms of frequency response sample, capital H of k, we required only up to 7 at the most, okay, 4 plus 3 in the transition band, or 8 depending on what you want. In the impulse response calculation you require up to 7, only the first half, the next half would be by linear phase constraint, they would be equal, okay. So, if you do that, the final results are like this. This shows the frequency response without any sample in the transition, that is abrupt. And you notice that there is Gibbs phenomenon here, there is Gibbs phenomenon here. This is with one sample. Gibbs phenomenon has been considerably reduced, but at the cost of what? You see, the 0 occurs here at 0.26 or something. Here it goes much beyond, that is its widening, and this effect will be experienced whenever there is a Gibbs phenomenon. This contains 2 samples and this contains 3 samples. If you use more, well, you are widening your pass band, but you are achieving a better pass band response, okay. So, it is a matter of compromise, what you want to give up and what you want to achieve. Finally, I promised that I will give you some formulas for estimating, I do not know if this is visible, For yes, is it visible? Okay, I have given you a copy, do not worry. But these are the best formulas that are known so far. You see, for a low pass filter which apparently is applicable to high pass also, okay, the estimation of the order is slightly complicated. It requires a little bit of calculation, but once you program it, it's not a problem. The only thing that one has to be careful is that the symbols are slightly different here. Our delta p, in our case delta p was the smallest transmission in the pass band. Here delta p is the ripple, that is the difference between the maximum and the minimum. You have to be careful about this. If the maximum is 1, then 1 minus delta p is the minimum transmission in the pass band. So this delta p is the pass band ripple, delta s remains the same. On the other hand, in FIR, as you know, the usual procedure is to specify 1 plus delta 1 and 1 minus delta 1. If that is the specification, then delta p you have to calculate twice delta 1. That is correct. All right. So delta p and delta s are different, and delta f is as defined earlier, that is omega p minus, I beg your pardon, omega s minus omega p divided by twice pi. Okay, this is delta f, and in the case of a high pass filter, it is omega p minus omega s divided by 2 pi. Is the point clear? So you have to be careful about this. In the case of a band pass filter, which apparently is applicable to band stop also, the calculations are a little more, no, it's almost the same complexity. You have to calculate 2 functions here and 2 functions here. Delta p, delta s have the same interpretation, except that in this case the transition band delta f, the delta f is now, yes, what should be delta f? It is the transition weight normalized to the sampling frequency. So it is omega p2 minus, no, that is not the, in a band pass filter it is not the transition frequency, transition band. Don't make a mistake. In a band pass filter, it would be omega p1 minus omega s1 divided by 2 pi, and you have to make sure that these two are equal, that is omega s2 minus omega p2 by 2 pi. You have to make sure that they are equal. If they are not equal, then you have to adjust them. Is this caution registered with you? No? In the case of a band pass filter, delta f is transition bandwidth. Now there are 2 transitions here. Okay? So you have to adjust the 2 transitions to be equal by adjusting either omega s1 or omega s2. Do not change omega p1 or omega p2. Agreed? Then only you can apply this formula. Even if you make a mistake here, the formula is only an estimate. Only thing is it will be widely divergent, whereas if you exercise this, it may be slightly easier. Life may be slightly easier to converge on what you ultimately want. In the case of a band stop filter, you shall have to exercise the same caution. In the case of a band stop filter, delta f would be omega s1 minus omega p1 divided by 2 pi, which has to be adjusted to be equal to omega p2 minus omega s2 divided by 2 pi. Agreed? I am not writing these words of caution in black and white. I hope you would be able to do this when confronted with a situation. These are the only formulas known. There is no other way. There is no other way. And it is strongly advised that you first estimate the order. Depending on the order that is required, you will make your calculation. If the order is small, then you do not require those h1 of e to the j omega, that summation formula, and therefore your efforts will be much less. So you have to do this, and that brings us to the close of this course. What we did in the course was about 1/3 of the semester we spent in this discrete time signals and systems. We considered them in the time domain, we considered them in the frequency domain. In the frequency domain we talked of Fourier transform, discrete Fourier transform and Z transform. In the time domain we showed how to calculate the convolution, we gave some tricks, and then the rest of the semester we spent on filters. First we discussed digital filter structures, and then as a prelude to digital filter design we did fairly thoroughly analog filter design, and then we talked about digital filter design, IIR as well as FIR. We only discussed the analytical techniques. The computer aided techniques are modifications of optimization procedures, numerical optimization procedures, and in FIR Remez exchange algorithm is very much used, that you can get in any book or any program. What we propose to do in the next course, as and when it is offered, is we will start with first computation of DFT, that is we will do FFT and also number theoretic transforms, which offer a better means of speeding up the computation of DFT. There is also a technique called WFT, Winograd Fourier transform. Winograd gave an algorithm which is still better. Then we propose to do finite word length effects and how to minimize this. We will come across different kinds of structures in finite word length. When we do finite word length effects, the minimization, and then multi-rate DSP, which is a very hot topic at the current time, and most of the equipment comes with multi-rate. At different locations there are different sampling frequencies to suit the, and then the interface between the two, decimation and interpolation, they are required, and it poses a challenging problem in filter design, which the procedures that we have given will help. Then we shall do wavelet theory in some details and some selected applications of digital signal processing. It is proposed to be done in a second course, DSP2. And with that we close this course.